I'm going to explain the use of the mean systemic filling pressure. So if you imagine a circuit, okay, and let's say that this is a circular blood vessel, circulatory system. Well, we can start with just a simple piece of that system. And if we fill up the elastic tube, which are your blood vessels, if you fill it up to here, it's not going to really cause the transmural pressure to rise above zero. Let's say you fill it up to here, and then let's say you fill it up all the way to the edge of the blood vessel without distending it. The transmural pressure will still be zero. But once you add enough blood volume into the system to the point where it stretches the vascular walls, that stretching is going to cause an elastic rebound inward and cause a pressure to build inside the blood vessel. And so it turns out that when you do this in a human being, you actually have about 1 liter extra blood volume in your circuit, such that it distends the walls, which causes a rebound recoil that causes the pressure of 7 millimeters of mercury. So when we stop the heart, if we introduce a heart over here, we stop the heart and let the system equilibrate after a few minutes, and then we measure the pressure here, 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 anywhere along the circuit, whether it's the arterial side or the venous side. You're going to see an average pressure of about 7 millimeters of mercury, and we call that pressure at zero flow, the mean systemic filling pressure. And so the circulatory system is not just the blood vessels, but is also the cardiopulmonary organ structures as well. And so when you add the heart into the equation, we know that the right atrium, which is right here, typically for human beings has a right atrial pressure of 0, which means that the venous return gradient is going to be 7 millimeters of mercury, 7 minus 0. And that will cause flow to return to the heart even when the heart is stopped. Okay, so knowing that, how does that apply to clinical situations? So we know that venous return determines cardiac output in a closed circuit. And the mathematical equation for venous return, which is in liters per minute conventionally, is mean systemic filling pressure minus the right atrial pressure divided by the resistance to venous return, which is usually negligible. And so the msfp is typically 7 millimeters of mercury minus 0. And the resistance to venous return is about 1.4 millimeters of mercury per liter of blood. And this is going to give a value of 5 liters per minute, which is a typical cardiac output, which in this case is the venous return. So venous return should equal cardiac output. The left ventricle should only be pumping exactly how much volume return to it from the right side of the heart. So the clinical part here is knowing that there is an intrinsic 7 millimeters of mercury of mean systemic filling pressure. That means that the variables that affect mean systemic filling pressure are the total blood volume in the circuit as well as the venous tone. Okay, so if we increase the venous tone through venous constriction, we're going to increase the mean systemic filling pressure because of the squeezing, pushing the blood back to the heart, pushing more blood back to the heart. And likewise, if we stick an IV and introduce IV fluid, such as lactated ringers, to quote-unquote tank up the system, we can also increase the blood volume and hence the mean systemic filling pressure. We always want to keep the right atrial pressure as low as possible. So if the patient's blood pressure is low or the cardiac output is low, we want to make sure that there is nothing compressing the right atrium or causing the right atrial pressure to be increased. And the forces can be either too much blood volume in the right atrium, which will increase the right atrial pressure. There can be tamponade pushing from the outside, or pneumothorax pushing from the outside, collapsing the right atrial wall, thus increasing the internal right atrial pressure. There can also be pulmonary artery hypertension from either PE, which results in the RV not being able to eject the blood forward, and then that extra volume in the right ventricle will be transmitted up into the right atrium, thus increasing the right atrial pressure, which will again decrease the venous return.